GE, super easy. Okay? Ethan sent you an email, you should have gotten it, where he calls out there's an app out there, right? And I've not used it, but I've seen students use it in the past, and I think it's accurate. I'm not going to endorse it. It's probably accurate. If it's not, I do have a hard copy, kind of flashcard title. It's on this pink handout that has the same information. So you want to quiz yourself, so you're ready to recognize the side chains in all 20 and the three letters. All right, let's take another look at point number 2. I'd like you to know not 1, not 2, but 3 different ways to make alpha amino acids. Okay? Let me ask us our favorite question. Are you feeling what? And what's the answer? Yes. Yeah, me too. It turns out that I'm not going to hold you to the mechanisms for these first 2. Now, if you see the second one, you will go, what were you smoking when you wrote that down? What I was smoking was that this used to be the very last chapter, next to the very last chapter that was covered in this textbook before they changed the chapter order. And what I was trying to show students was that this chapter basically had nothing new in it. And that's still true, okay? There's nothing new, but what I was trying to show is what we already know about the malonic ester synthesis in an earlier chapter. It's the same day what? Okay? So nothing different. It's just an application of that malonic ester synthesis. But I also began to realize after a few years of trying it that maybe students' memories were about as bad as mine was, you guys age. And maybe people weren't able to remember the same day thing, even though it is the same day thing. So I said, what the heck, let's not require people to know it. I'm going to briefly gloss over. This one is super easy. It is just an SN2 substitution. You take an alpha bromo carboxylic acid, add excess ammonia, and NH3 displaces the Br2 in an SN2. Before I move on, very quickly, why do you suppose you need excess ammonia? What would happen if you only used one equivalent of ammonia? Trick question. No, really trick. There's a reason it requires excess. It's related to why we have the Gabriel synthesis. You guys remember that? What the beauty of the Gabriel synthesis is? No. Well, will you remember by the time we go to Rome? Why do we have the Gabriel synthesis? What's the right answer? Yes. Okay, good. I'm glad. The Gabriel synthesis allows you to avoid polyalkylation. If you add this in a 1-to-1 ratio, you're going to get that nitrogen with not 1, not 2, not 3, but up to 4 amino acid groups attached to it, and that's a dead end. Okay, so excess ammonia is required. I'm not going to test you on that per se, but if this happens to make it into the submarine, you will see this plus ammonia and in parentheses either the word excess or maybe 5, 10, 15, 20, 30 equivalent, something like that. Don't let those throw you. Don't be thinking, oh, he's putting all this in, then more than one thing must happen. And the answer to that idea is no. Okay, the excess is just to avoid what? Why do we throw in excess? To avoid what? Polyalkylation. You got it. Okay. So we won't worry about the mechanism. Let's take a look at reactions B and C. I think C is worth knowing. There's the flashcards I gave you. Don't worry about these for now, but you do want to go through these, be able to recognize the side chains, and also know the 3 letter acronyms. So there they are. This is the mechanism for, it's not the mechanism. This is just the reaction itself. These you should know. The malonic ester synthesis of amino acids starts with this beginning starting material with an acetyl protecting group. So, that's dihydroacetic acid on an NH2. Notice that there is a nitrogen on the alpha carbon. You have 2 ester groups. So it's not quite an amino acid, but if we deprotonate here with a base and then alkylate with an R group, so as an SN2, you get to here. We heat with aqueous acid and then pull out our scalpel because we're going to do what operation? CO2ectomy. You see it? We're just cutting off CO2. Did we ever talk about that reaction? Yes. Yeah. We talk about the mechanism. Yes, we did. We'll see it again in a second. The good news is this time it's going to have a big X to it. All right. Strecker synthesis. I've warned you guys about this a few times. I think I actually pulled it from the last exam, family trip, but this time it's definitely making it into the boat. Okay? Definitely getting into a submarine. And what it involves is treating an aldehyde. Okay? Or it could be a ketone, but then it'd be a dialkylated. There's usually an aldehyde to give you a monoalkylated amino acid. We get a condensation reaction. We lasso out H2O. Under acidic conditions, 1H is still there. This is just an imine. Do we know how to make imines? Yes. Okay. So we make an imine with the plus charge on the end. That makes this carbon quite electrophilic. So where cyanide comes along and says, it blows the horn, we put down the microphone and record it, blows the horn. I'm electron rich, you're electron poor, tax that carbon 2 in, 2 out. We make that guy, which looks a whole lot like a cyanohydrin, very close relative, true aqueous acid that hydrolyzes the cetron one in, gives you beer. Okay. All right. Are you still feeling lucky? Yes. Good. We're going to skip the mechanism of that part. We'll skip that part. But this part, I think, is worth knowing and is very well known. All right. We're going to do what I call Dead Poet Society. That's a verb. We're going to Dead Poet Society this slide. So go ahead and on number 3, go ahead and cross it out. Okay. Cross it out lightly because it's worthwhile. It shows the mechanism for amino acid synthesis from, this is the SN2 substitution. So don't worry about that one. You know what I'm talking about with Dead Poet Society, right? You ever see that movie? Yeah? The English professor in the poetry textbook? If you've not seen that movie, you can go see it. First day of class, what did he have the kids do? You guys remember this? Rip the page out. Take a look and rip the pages out. We're doing a similar thing. Okay? But I would encourage you, as you put X's through, put a big X through. Let me find the page so you're putting it through the right place. So we're looking at mechanism 3, part B. So be on page 2. I'm going to put a big X through that. That is just the mechanism for the malonic ester synthesis, which we already studied. Okay? Which years ago I thought, well, this is a gift. People will like this and be grateful that, we're just covering something we already know. However, it's got 10 steps and actually it's got more than that. Maybe that's 10. It's got a lot, whatever it's got. People were not as enthusiastic about it as I was. Woo! Okay, that's the last step. Cross those out. And yes, old man, go ahead, give me a big hand, that's okay. Could you stand up while you do that? I did that last summer. Class gave me a standing ovation. So, of course, you guys are getting told, right? All right, let's continue with our Dead Poet Society stuff. This one, unfortunately, I'd like you to not cross out. This is on page, I think it's the next page, page 3. Turn it over, Strecker mechanism. I'd like you to know this. Okay, it's on page 3. Page 3, page 3 right there, the right hand corner. Back page, I guess, page 1, back page, number 3, top corner. All right, the first part of the Strecker is literally just making an iminium. Technically, this is a protonated imine. But everything from here to there, you guys already know because you have practiced and seen and understood the cowboy chemistry. You know how to do it, right? So, perfect. You just stop here with protonated imine. And then remember, in the last step, what you know, a cyanide comes along, attacks that carbon 2 in, 2 out, and you make this guy. which is analogous to a cyanohydrin. So there's nothing new here, just applying what we already know. And since we are feeling lucky, we get to take our big red markers out, and we get to cross out, it looks like steps 6. So this is still on page 3. 6 through 8, go ahead and cross those out. Those show the mechanism for hydrolysis of the C triple bond N, which is an important mechanism, but it's kind of, at this point, kind of maybe excess baggage. Maybe I'll ask you a personal question. Are you beginning to feel like you're on mechanism overload by now? Are you? That's what I thought, but unfortunately, there's more to come. Therefore, we're going to cut you a little slack on this one. Don't worry about this one. But what I would like to point out to you is after the C-triple-N is protonated, water attacks, eventually we get to this guy, okay, which is just a protonate. Let me erase that proton. Let's erase cloud eraser. Erase. What is that piece right there left over? What is it? Is it an ester, an anhydride, a thioester, an acyl chloride? What is it? It's just an amide. That's all that is. So you add aqueous acid to that nitrile, eventually it forms an amide. Upon continued heating, on the next page, let's take a look at the next page. Let's take a guess. Will the next page have a big red X in it? Yeah! Yes! Yes, Virginia, there is a Santa Claus. Okay! There's on the North Pole. So don't worry about this aspect of that hydrolysis. But the bottom line is that C-triple bond N in the back, right here, that does become a CO2H. You need to know that. On hydrolysis, that C-triple bond N becomes a CO2H. If you want to, let me stop if you look at the mechanism, but I'm saying you don't have to know it. Okay? All right, 2 big red X's. And are we feeling lucky? Yeah! Okay, yes, we are. Remember, write the sticky notes. Peterson, 3 pieces of paper in that name. Long name. Thank you. Okay. However, we'll go ahead and cross this out. This is a mechanism for DCC catalyzed coupling of amine to carboxylic acid. I don't want you to ignore the reaction. I'm cutting you some slack on the mechanism. Okay? So with that as a backdrop, do you think, if you were to bet, would you wager that maybe this is going to make it into the submarine, do you think? The reaction itself? Yeah. Super useful in peptide chemistry. This reagent is called DCC. Maybe on Wednesday, maybe today. I don't feel like writing it. It takes a while to write, but I can tell you what DCC stands for. It stands for dicyclohexyl carbodiamide. All right, well, later it takes a while. But DCC, I'd like you to know the structure and the structure of that, which is called DCU. Dicyclohexyl, there's 2 cyclohexyls, and this group is a urea. So know the structures of DCC and DCU, okay, because those are definitely making it in the submarine. They're a very, very important part of peptide chemistry. Why? Oh, thanks for asking, because I'm going to answer. Why? You ask, why? Oh, thank you. Oh, I'm sure. Okay, I'll tell you. You're going to twist my arm, I'll tell you why. Okay. Why is DCC and why are the answer to DCU is coming first in a few days, probably on Wednesday, but for right now I'll tell you about DCC. What DCC does is it reacts with carboxylic acids. That's this one here. Let me ask you, what does DCC do? React with carboxylic acids. You guys are super on top of it. Exactly, yeah. And it forms this guy. First protonates it. Then the carboxylate attacks that carbon, boom, 2 and 2 out, and we form this species. I want you to look at that and digest it for a second. Again, I'm not going to ask you to recall this from memory. But what I want you to notice is I've used a red color here, red there, red there. Yellowish green here, yellowish green there, yellowish green there, blue here, blue there. I used that color scheme in this chapter on acyl transfer. Remember this? Where the top of the board I had over here on this board, an acyl transfer, I had acyl chlorides at the top. Remember this? What came next? Under acyl chlorides, remember? Anhydride, thioesters, then esters, then amides, carboxylic acids. Those are acyl transfers. This guy is kind of like an anhydride. If I redraw it like that, we have a carbonyl here, still no O. An ester would actually, excuse me, anhydride would actually have a carbonyl O right there. So it looks a whole lot like an anhydride. What would you guess about how it reacts? And there's the answer right there. A whole lot like an anhydride. Wow. You see it? Because structurally, what? It's a whole lot like an anhydride. Of course it's going to do what an anhydride does. It's a whole lot like it. It's actually a special kind of anhydride. It's not a carboxylic anhydride because this piece is not a carboxylic acid. But what this yellow piece does, which came from DCC, help me out, is it activates. It activates the acyl group. Okay, it activates. It's a reactivation effort. We're activating this guy towards nucleophilic attack. Nucleophile comes in, two out. We make a tetrahedral intermediate. Have we ever heard of tetrahedral intermediates? Yes. About a bazillion times, right? Okay, fantastic. We know they're not very stable. They collapse quickly. And bottom line is, after everything's said and done, we transfer the acyl group, okay, off of the OH. The O goes on to what used to be DCC. That's where that O comes from. It's right there. This used to be DCC. That C picks up that O. Or she blows. Yeah? Or she blows. Okay, what kind of talk is that? Whaler's talk. Okay? That's the spout. That's where the O went. Right there, that carbon. And last but not least, we have transferred that acyl group to the end to make an amide. Okay. Is that important to this chapter? Yes. How much of this chapter is about amide forming reactions? 99%. Okay. But what do we have to worry about? The other 99%. This is a big part of it. Okay. All right, that's my segue into two other ways we know how we're making amino acids. In fact, before I do that, let's go ahead and write on the board what we remember about acyl transfer. So that's the top one. Then we have this one. We're going to skip thioesters to get regular esters and come to amides. So what we're talking about is how the heck we make amides, that bond right there. How do we do that in most cases as above? So let me ask you, if I wanted to go from this one to that one, what would I treat that with to make that? An amine, right? Super easy, okay? What else could we do to make this? Treat the anhydride with what? An amine. How about what we can treat that with? An amine. Get it? Good. Get it? Good. All right. Fantastic. We treat any of those with amines, we'll make amides. Here are two methods for making amides. Common ones, treat an ester with an amine. By the way, in an exam setting, this is highly illegal. I'm showing A coming in, B going up. I'm skipping the tetrahedral intermediate, C coming down, and D leading. Don't do that. Okay, in an exam setting, don't put 4 steps on one structure. You okay with that? This is highly illegal in an exam setting. You say, well, why do I get to do it in class? Because I don't want to take the space, and I know darn well this is not a one-step reaction. I know that. But in an exam setting, you want to show A attacking the carbon, B going up, show the tetrahedral intermediate, then show the electrons coming down and kicking off an alkoxide. That gives you the amide. Okay, from an ester. Similarly, we treat an acyl chloride as amine, the same thing amides. Okay? So with that as a backdrop, if we're trying to connect the carboxylic acid of an amino acid with the NH2 of another amino acid to make an amide bond between two amino acids, which, by the way, what do we call that special kind of an amide bond? The answer is on the slide. What do we call that bond right there?
Peptide.
Peptide bond. When you have an amide between amino acids, they call it peptide. Why not just call it amide between amino acids? Because that takes 30 seconds to say amide between amino acids, so it's just easier to say peptide. But that's what the word peptide means, is at least one amide bond between two amino acids. If you have three amino acids, they call that a tripeptide. If there are four, they call it a tetrapeptide. If they have five, what do you think they call it? Hepta, 6 hexa, 7 hepta, 8 octa, 9 nona, all the way up to, after about 20, they start calling an oligopeptide. I'm not going to test you on that, but that's what that word means. Amide between amino acids. All right. How can we make an amide between two alpha amino acids? That is the other 99%. Actually, that's the first 99% of what this chapter is about. How to make peptide bonds between amino acids. Okay with that? It's all about making peptide bonds between amino acids. Seems like gotta be super easy, right? Yeah. Oh. Seems like it at face value, but what class is this? OChem. So can it be easy? Yeah. But it's not that hard. And I will take you step by step, and by the time you see it, yeah, actually it is easy. It's actually not that tough. Let me show you an approach. Okay? Here would be an approach. We take and treat this with thionyl chloride to make the acyl chloride. Okay. Then we treat it with that amino acid, and we ask that NH2 to attack that carbon to make the peptide bond. That is an feasible or possible approach. But let me ask you this tantalizing question. And will you agree that is that tantalizing? I hope say yes. By the way, I've got a fresh donut up in my office that was made over the weekend by one of my colleagues. So you'll let for a few days. Bring it on Wednesday. Whoever answers that question right gets that donut. Wow. Isn't that tantalizing? Would this work as written, do you think?
No.
No. Why?
No working.
Here's a hint. We got a bunch of little red flies, red gnats, red dots floating around. And even though you want that pair of red dots to attack that cardinal, even though that's what you want to have happen, what you suppose will happen? All three of them. Okay. So all what's going to break loose? Don't. You got to clean this up. What's going to break loose? Using BYU. He double what?
Q.
Q. All heck's going to break loose. Okay. All heck is going to break loose if you try to do this. And what you're going to get instead of the desired amide bond, okay, is a big mess. And we just said why. What's going to happen is you're going to get dimerization of the two acyl chlorides to make that dimer. This is the desired reaction. You're going to get some of that. And remember, do not use, in an exam setting, don't show all four of those on the same structure. I'm just doing this so I don't want to burn up too many PowerPoint pages, okay? And last but not least, the OH, the splicing unit here can react and form an anhydride. Okay, take a look at these two, acyl chloride and anhydride. Where do they come on the reactivity chart? Look over there at that board, acyl chloride, where are they? They're up there, right? Yeah? We just made another acyl chloride in situ and an anhydride. What's to stop this from reacting with that, or reacting with another one of these, or one of these reacting with that? You're going to get a trimer, you're going to get this dimer, you're going to get that. That's the one you want, but the bottom line is you're going to get a big mess. Okay? All right. Well, what do you do to solve a mess like this? What are you going to do? Call who? Ghostbusters. Ghostbusters, okay? I should have put a ghost in there on advance. They're not advancing. What's the solution? There is a solution. And the fact of the matter is, I Googled this to make sure this is true. It turns out that apparently chemists have all the solutions. In case you were wondering, that is true. And I even Hills and McCaffrey certain said it multiple times. That's not just AI. Chemists have all the solutions. Okay? Here is the solution to that problem. It may not be all the solutions. A lot of the solutions for sure. What's the solution to the problem we've been talking about? Protecting groups. Have we talked about protecting groups in the previous chapter? Yeah. What's their purpose? Protect. Perfect. Ask a stupid question, right? Get a smart answer. Very smart. Okay, protecting groups transiently convert a functional group into some other functional group, right? And the purpose is to make that other functional group not react, to not do something that you don't want it to do. We don't want to have that big mess of products. We want only one of the 4 or 5 that I showed you could have. We only want one of those to have. So the solution is to protect the offending reactive nucleophiles and make them so they are no longer reactive. Okay? So we don't want this guy to be an amine. We don't want it to react as an amine. We only want this end to be reactive. So we're going to protect that nitrogen with, I'm going to give you the structures of, right now I'm using the abbreviation P, but the idea is you protect that NH2 so that it is no longer an NH2. Okay, at the risk of boring you to tears, once I put this group on, what is this no longer? NH2. It's no longer an NH2. It will not act as a nucleophile. It's dead in the water. You will convert it into something else. I'm going to show you what the nature of P is in a minute. Okay. Right now it's top secret. Okay, we'll see. Okay. All right. While it's protected, we then add SOCO2. We can make an acyl chloride. Then we take this amino acid with this end protected. And this was not protected. It was an OH before. When it was an OH, the OH could react with that carbon. We don't want the OH to react with that carbon. We want to only make only one bond, and that one bond we want to make is right there. We want to make it between that carbonyl and that nitrogen. Okay, so you get that carbonyl, and that nitrogen. That's the only bond we want to form. That's the only reaction we want to have happen. Okay, we'll highlight that with red. And we can achieve that only by protecting that NH2, making it so it's no longer an NH2, and protecting this OH and making it so it's no longer an OH. It's now, what do we call this functional group right here? What is that? That's an ester. We don't want it to be an acid. If it were an acid, the acid could react with that carbon, and we would get a mixture of products, and we would not get a clean formation at all. Okay? Once this reaction occurs, then the job becomes removing protective groups. And that's true for all protective groups. There are groups you can put on transiently, so they mask the reactivity you don't want to happen, then it can be taken off easily. Okay? All right, cool. We've now made the alagly dipeptide. This is alanine, S-glycine, and they call it a dipeptide because there are 2 amino acids in it. I guess there's no such thing as a monopeptide because you think that would be the simplest definition, because in order to be a peptide, you have to have an amide bond between 2 of them. They still call it a dipeptide. There's 2 of them. Okay. Let's take a look at what some of those protecting groups are on nitrogen. Okay, this should be, let's take out our handy dandy green colored handout, which I colored green just to kind of remind me of all the trees we killed. I didn't copy this till today because I thought I could possibly get away without it. I feel bad, I really do, especially after Elder Crusade's talk on Tuesday about protecting the environment, which I've not fully listened to, but I know I've talked about that before. Yeah, so I killed some trees. We're now on page 5 of the handout. Okay. From this point on, there are no red axes. Sorry. Sorry, this is OChem. Okay, there's a lot to cover here. All right. This is page 5 of your handout. These are ways to protect the amino group. Luckily, there are only 3. 1, 2, 3. Only 3. Whew, thank goodness, only 3. Check them out. One is called the Bach group. One is called FMOC, and one is called CBZ. Bach, FMOC, CBZ. Bach, FMOC, CBZ. Just make some flashcards, study it a few times. I would like you to know the structure of the reagents for putting those groups on. Bach is just Bach anhydride. FMOC is just fluorinomethyl oxycarbonyl. That's an acyl chloride. That's an anhydride. That's an acyl chloride. There is nothing new here. Acyl chlorides, anhydrides, we already talked about. What is new is the nature of the argument. If you know that Bach stands for tert-butyl oxycarbonyl, tert-butyl oxycarbonyl. Bach, yes, you remember, tert-butyl oxycarbonyl. Tert-butyl oxycarbonyl. We learn by repetition. What group is that?
Tert-butyl.
What's that? Oxy what? Carbonyl. Tert-butyl oxycarbonyl. Bach. Okay. And all the transfers we're going to see in the next slide is this acyl group. There's the acyl group. That, what does that become in that reaction? That's the acyl group. That's the weight group. We'll see in a second. Fluorinomethyl oxycarbonyl, FMOC. Fluorinomethyl oxycarbonyl. Fluorinomethyl oxycarbonyl. Okay, the reagent is fluoronyl oxycarbonyl chloride. And that acyl transfer group transfers, blah, blah, blah. And last but not least, carbonyl benzyloxy. Carbonyl benzyloxy. It's named a little bit different than the others, admittedly, but that's the common name, CBZ. And these are the three workhorses in making synthetic peptides, yes. I don't care if there's three, because there's way more than three. And then you're going to think, oh, thank you only showed me three. If any of you end up doing any research at all in peptide chemistry, these are the workhorses. Bach, FMOC, and CBZ are commonly used in making synthetic peptides. And by the way, there is a ton of biologically relevant research that's done with unnatural peptides. It is true you can probably clone anything that's bigger than 100 amino acids. You can probably clone it using it synthetically. But there are some even then you have to make a synthetic animal or synthetic piece. On Wednesday, I'll show you. We're going to talk about how you make large polypeptides using this particular strategy. So right now we're just doing chopsticks, but the three are the three most common. Yes. They all do the same thing. Let me show you what they do. Is they transfer the red piece in an acyl transfer reaction, yeah, to the blue piece. So, using the same kind of color scheme that we use in the chapter on acyl transfer, this should seem familiar. I use red for acyl, blue for the nucleophile, and yellow for what? The leaving group. See it? That's going to go off as a leaving group. The red acyl will react with the blue end. Where does the other H on the end go? Remember? There were two H's. Where do they go? The nucleophile has two H's. Where does it go? With the leaving group. I don't care that you show the leaving group. It turns out that's spontaneously decomposed to CO2. Not going to go there. That's a complicated aspect of this, but that is true. Here, the leaving group is Cl. Acyl transfers to the blue end. One of those H's goes off with this to make HCl. I didn't write that there because it is not organic, and organic chemists are what? Snobs. Snobs when it comes to atoms, okay? Atomic snobs. Same thing here, the acyl group transfers to the blue end, and it only comes off of this to make HCl. Okay. The purpose of all three of these is to convert the NH2 of any amino acid, those R groups are any of the 20, okay? Convert the NH2 into a protected NH2, which is called technically a carbamate. I'm not going to test you on that word, carbamate. But when you have an N and an O and a carbonyl, you call that a carbamate or a urethane. Ever hear of polyurethane? Polyurethane has multiple units like that, not made from amino acids. The urethane is an N-acetyl-O. That's the urethane functionality. All these are urethanes. Since they're urethanes, they now no longer react like amines. Because guess what? They ain't amines anymore. That ain't a word, right? And we ain't supposed to say it, but we're gonna, because these ain't amines. Can you remember that? Why did we put those groups on? So those, well, what? Not be, that's the wrong conjugation, but future tense of ain't. Make it so we can say that those ain't what? They ain't amines. What are they now? They're urethanes. I don't care if you know what they're urethanes, but they are. Okay, but they ain't amines. That's the important thing. They are no longer amines. Since they're no longer amines, they will not do what amines do, which is act as a nucleophile. Okay? They are protected. Those nitrogens are protected. All right. We're going to also now talk about how you protect the carboxyl group of amino acid. And this one, hallelujah, thank goodness. This is like, well, I'm going to see if I've got a fever. This is atypically simple. I'm like, wait a minute, am I in the right room? You go out and look, check and see if I'm in the right room. This, okay, this is atypically simple. Look at this. This is how we protect a carboxylic acid and make it so it will no longer react like a carboxylic. What are we doing to the carboxylic acid? What are we doing to it? Turning them into esters. Do we know how to do that? Did we ever talk about the Fischer esterification? Yes, we did. Okay, so this is nothing new. Hallelujah. Thank goodness. I think you're going to see as you go through this. This is what I really like about this chapter, is it really kind of brings together a whole bunch of stuff we've been talking about previously, and now it's all in one place. We've seen it before. Okay? So, if we take a free amino acid treated with methanol and H+, it will undergo a particular kind of esterification. You guys remember the name of that esterification? It's named after a famous chemist who won the Nobel Prize. What's his name? Fischer, exactly. Fischer esterification. We'll cast out, reel it in. Fischer esterification. Okay, same thing here. Now we're using a benzyl alcohol. So it's the same. You could use an ethyl alcohol, but usually it's methyl and benzyl. Okay? That's how you put them on. What we're going to see next. So that should be, I think, help me out, what page are we on? 6. Oh yeah, we just put them on. Now we have to talk about, oh, I skipped a noodle, didn't I? We're going to talk about how you take protecting groups off. Let me do this for 2 seconds, and then let's have some fun. We haven't looked at pictures from the class for a while. Let me just stop here and encourage you to look at pages 5 and 6, which talk about how you remove the protective group, because eventually you want to take the thing off. One of the aspects of protective groups is both go on and off. We'll come back to that. You go to page 108. Admittedly, this is from last summer, but I've got some from our class as well.